Hello everyone, my name is Sourav Garg and I'm going to present our research paper titled Delta Descriptors, Change-Based Place Representation for Robust Visual Localization. This collaborative research work was funded by an AOARD grant. Visual localization is the task of estimating a robot's position in the world by using visual information. Given a collection of images as a reference map, one can match the currently observed image with those in the database to tell where they are. This is referred to as visual place recognition. One of the core elements of visual place recognition is the ability to meaningfully represent a place using a single image or a sequence of images. In many robotic applications, places are often observed as a sequence of images as demonstrated on the left. The aim of this research is to develop robust place representations that can leverage this sequential information and at the same time have robustness against extreme appearance variations, for example day versus night or summer versus winter as depicted here. The existing literature for visual place recognition has mainly focused on developing single image-based descriptors, which are then combined with sequence matching methods which mainly operate on the pairwise similarity scores obtained from single image matching. As an orthogonal approach, we propose to use sequence-based spatiotemporal descriptors, which can then be combined with existing sequential score aggregation techniques, but this time utilizing math scores obtained via pairwise sequential descriptor similarity. Before getting into the details of our proposed approach, we would first like to highlight the research gap through visualizations of state-of-the-art single image descriptors. The image on the right-hand side is a thumbnail of a video which we'll play shortly, but first let's look at what is what. We are going to visualize a high-dimensional single image descriptor, NetWheelAD, using its first three principal components. Note that this 3D plot does not represent GPS or INS trajectories, but low-dimensional image embeddings. The two colors, green and orange, represent two different car traverses from Oxford, where one was captured in autumn and the other one in winters, where images from both the traverses have one-to-one correspondences. As we're plotting a sequence of 3D embeddings for each color, we also perform a sliding window average in temporal dimension for a smoother visualization. The primary thing to observe in this video is the offset between the green and orange segments, which leads to poor performance, and ideally one would expect these two segments to be exactly aligned with each other. We can observe that as the vehicle navigates through different surroundings, the offset between their sequential embeddings varies, and in some cases it is quite huge. This occurs primarily due to variations in scene appearance conditions, including those due to different season, and in part due to dynamic objects like cars, pedestrians, and temporary structural changes. Now consider this snapshot from our visualization. We can observe that although there is an offset in the spatiotemporal embeddings, the shape of these sequential embeddings remains the same across two traverses. This shape characteristic can be captured through our proposed delta descriptors. Delta descriptor is defined as a high-dimensional difference vector that measures changes across places observed along a route. As illustrated on the right-hand side, we consider a smooth signal and then compute difference vectors across a window of given sequence length. This operation is performed independently on different descriptor dimensions. Consider a sequence of corresponding images from two different traverses, and this time we consider a challenging scenario of recognizing places across an autumn night and a winter day. We plot the raw values of one of the descriptor dimensions against its image index for a portion of the traversed route. The images in this case are uniformly separated by 0.5 meters, and the orange and blue color represents the night and day traverse respectively. It can be observed that there exists frame-to-frame volatility in the descriptor values within a traverse. Secondly, there exists a non-uniform offset between the descriptor values across traverses, that is, when comparing the orange and blue curves. Using the raw descriptor values, we can compute the smooth descriptors using sliding window averaging. We use this version of the signal as one of the baselines in our later performance comparisons. It can be observed that the smooth descriptors maintain their overall shape but still suffer from the offset problem. As indicated previously, we compute delta descriptors through smooth signals by measuring the changes in the form of difference calculated across a window of a given sequence length. This operation is equivalent to computing slope of the signal but using points separated by a window. It can be observed that delta descriptor gets rid of the offset and the blue and the orange curves are now better aligned with each other. Although we presented the computation of delta descriptors according to our intuition and initial observations, it is possible to directly compute delta descriptors through the raw descriptors in a simplified manner. This is done using 1D temporal convolution with predefined weights. More details on this can be found in the paper. As we only looked at one particular descriptor dimension earlier, here we visualize some more descriptor dimensions that highlight the volatility and offset problem with the original raw and smooth descriptors, and further showcase the level of alignment achieved between the descriptors of two traverses by representing in its delta form. After computing delta descriptors independently for given two traverses, we use cosine distance to match these descriptors across these traverses, and then obtain the distance matrix as shown here in green. On top of these distance matrices, we have plotted the matches in red color, which are obtained based on the lowest cosine distance of a query descriptor when compared against all the descriptors in the reference database. The ground truth matches for queries lie on the diagonal of the distance matrix. It can be observed that using delta descriptor, number of false matches, that is the off-diagonal ones, can be significantly reduced. While discussing the prior literature, we highlighted two different ways of leveraging sequential information inherent within the problem of visual place recognition. Given these two unique ways, we explored the four possible combinations of using sequential information to improve performance. The legend box on the left-hand side depicts the descriptor type using images and the score aggregation strategy type with orange dots. Given a single image descriptor and without any score aggregation, dealing with extreme variance variations often comes with perceptual aliasing, as can be seen here on the right with numerous off-diagonal orange points. Using sequential score aggregation on top of the previous case, it improves performance. And instead of using sequential score aggregation, if we only use a sequential descriptor, that is the case for delta descriptors, we can observe that performance is much higher than the top left matrix. Finally, combining sequential descriptors with sequential score aggregation achieves state-of-the-art performance. Here we compare precision recall performance for the raw, smooth, and delta descriptors. It can be observed that for challenging scenarios like summer versus winter or night versus day, delta descriptors and its combination with sequence score matching, represented in green, consistently achieve high performance. We further analyze the characteristics of delta descriptors through a number of experiments like suitability to PCA type dimension reduction, effect of varying camera velocity, and the effect of temporal coherency versus the order of observations. We will look at these one by one. When performing PCA reduction using the reference database as the training set, the query descriptors may not always follow the same descriptor distribution due to difference in appearance conditions like day versus night. In this plot, we show that due to data centering operation, performance of raw descriptors suffers even when retaining all the components after PCA transformation. As delta descriptors operate in a different space, it is more robust to such dimension reduction methods, particularly when it includes data centering. In our experiments and visualizations, we so far assumed a uniform metric separation between consecutive image frames. In practice, this can be achieved through visual odometry. However, we consider the scenario where frame separation is not modified to study the effect of natural variations in camera velocity both within and across the traverses. In the plot for localization radii less than 25 meters, dashed green line, that is the delta descriptors, perform better than the solid blue line, that is the raw descriptors with sequential score matching. For localization radii greater than 25 meters, the performance loss for delta descriptors is compensated by its combination with sequential score matching, that is the solid green line. To further improve the robustness of delta descriptors to variations in camera velocity, we investigated the use of multiple delta descriptors based on the use of different sequence lengths, which is shown here in red, and it outperforms all other methods. More details on this can be found in the paper. In this experiment, we had attempted to decouple the effect of temporal coherency from the importance of the order of place observations. For this purpose, we shuffled the Nordland dataset such that within the reference and query traverse, no two consecutive images have any visual overlap, but preserving the new shuffled order across traverses. We found that for such scenarios, even a sequence length of 2 can significantly improve performance. This highlights that delta descriptors rely on the repeated order of observations than on the temporal coherency of observations. We also explored the suitability of delta descriptors with different underlying descriptor types. For example, an off-the-shelf global max pool layer of ResNet 50 and end-to-end trained networks for visual place recognition, including viewpoint invariant NetVLAD and viewpoint dependent AMOSNet and HybridNet. It can be observed that delta descriptors scale up the performance of all the underlying descriptors roughly in proportion to the performance of their raw descriptor counterparts. With this research, we found that sequential or temporal information can be leveraged to represent a place, which is quite different from its popular use for math score aggregation. Besides discussing the characteristics of delta descriptors, we also found that many different descriptor types can be used in the delta form to significantly improve place recognition performance. The current challenges for not just delta descriptors, but in general with the use of sequential information, consist in dealing with sensitivity to variable camera velocity and estimating the right sequential span for such methods. In future, we plan to explore more novel ways to estimate the shape of local time series patterns other than delta descriptors to dig deeper into the use of sequential information for place representation. The source code for delta descriptors is made publicly available. For any comments, suggestions, or queries, please contact at the email address provided. Thank you.